Hey everybody, this is Miss Boss. Today we're going to be talking about the properties of solids as well as the properties of solids, liquids, and gases. So, of course, we want to get started with the properties of solids because that's where we really are going to use our skills we've kind of put into place so far, and it's going to help us to apply it to the other two states of matter. So by the end of this, we want to be able to explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interaction between these particles. So what does all that mean? By the end of this, you should be able to tell me the connection between the macroscopic, meaning what we can see with our eye, properties of a substance, and the particulate level structure, meaning like at the molecule level, what does it look like, and how they interact. Okay, so it's the relationship between all three of those. All right, so states of matter. Recall for a few moments the three states of matter that we are going to think about in this course. Okay, you've got solids, you've got liquids, and you've got gases. So remember, in a solid, it's going to be a tightly packed, condensed particle level, right? In a liquid, you've got a little bit looser. It's still tighter than a gas, but looser than a solid, and it typically takes the form of the container that it's in. And then with the gas, you've got free floating particles. They're kind of going all over the place, right? And then they would fill the entire shape of the container that they're in. So we're going to think about properties related to the states of matter over the next few sections that we're learning about. All right. The solid and liquid states are called condensed states of matter. This is because their atoms are super close together, right? So solid and liquid, we're going to think of those as condensed because their atoms are super close together. Another major difference between solids, liquids versus gases is the presence of IMFs. Remember, intermolecular forces. All right, these IMFs are what determine the properties of these substances. So what all of this means is that because solids and liquids are more condensed, their particles actually have intermolecular forces. Versus when we look at a gas, those intermolecular forces ideally don't exist. All right. So when we talk about physical properties and IMFs, we're basically saying if substance A, so this is two substances together, right? If substance A has a blank, then substance B, okay, and then Y. So this is a because but so type of kind of way to think about this. So if substance A has a higher boiling point than substance B, then its intermolecular forces are stronger than substance B. So the higher the boiling point for a substance, the stronger the intermolecular forces. And this is because they require more energy to be overcome. Particles will not escape liquid to become gaseous until a higher temperature. Okay. Lower boiling point, weaker. So quite the opposite. Weaker ones do not need a lot of energy to be broken up. So the particles can easily escape the form they're in and become gaseous at a lower temperature. A higher melting point, stronger intermolecular forces. Hopefully you're noticing a pattern. All right. Stronger intermolecular forces require more energy to be overcome, to be broken, basically. So particles will require more energy, a higher temperature to spread out and become liquid. A lower melting point, weaker intermolecular forces do not require as much energy to overcome. Particles will be able to spread out and become liquid at a lower temperature. Higher vapor pressure, okay, is weaker. Weaker intermolecular forces are more easily broken, so particles will be able to escape liquid really quickly to become gas. And then a lower vapor pressure is a stronger, and this is because they're harder to break. The particles will often escape liquid surface less often. So really quick, just to clear a little bit of those up so we can pay attention to something. Boiling point, if you notice, refers specifically to liquids turning into gases, okay? So what it's literally saying is that it is way easier, okay, for a substance that has a low boiling point to go ahead and just become a gas because it doesn't need as much temperature. Okay, so the higher the boiling point substance requires, the stronger the intermolecular forces, which makes sense when you think about it. The higher the melting point, we're talking about solid to liquid. The higher the melting point, the stronger the intermolecular forces. And then with vapor pressure, I'm going to read this one more time because I want to make sure that you're interpreting this. Weaker IMFs are more easily overcome. Particles will be able to escape liquid surface more often to become gaseous. So hopefully you're noticing, right, when we're talking about vapor pressure, that vapor pressure and boiling point are actually connected to one another, but they work in the opposite directions. Meaning, if I have a higher vapor pressure, what that basically means is that there's way more vapor present in whatever I'm measuring, then that means there are weaker intermolecular forces. And that's because, remember, if something is easily turned into a vapor, which is a gas, then that means I didn't need a lot to boil it in the first place. Okay, so you gotta make sure you think about that and make those connections. All right, so types of solids. Okay, you've got ionic solids. They have strong attractions between positive and negative ions. All right, and I'm gonna try my best to keep my little box out of y'all's way. All right, so strong attractions between positive and negative ions. They can be alloys. They're held to metallic can be alloys held together by a mobile sea of electrons. So you guys remember this, right? There are two different forms of covalent solids. Okay, so this is really important. There are two different forms of covalent solids. All right. There's network covalent, which is held together by a network of covalent bonds, which are relatively strong. Network is either 2D or 3D layers. So I'm going to move this way a little bit because I want you guys to see something. All right, so 3D or 2D literally means three-dimensional or two-dimensional. Okay, these are covalent bonds, right? So covalent bonds literally mean that it's a nonmetal bonded with a nonmetal. And here's what's really important. Network covalent are stronger than the other type of covalent solid we're going to look at. Okay, so if you notice when we talk about a network, you see these different networks. So there's a 3D right here, 3D right here, 3D right here, and then these are 2D layers. So if you notice, those layers are flat two-dimensional layers. Okay, so this is more like when you sharpen a pencil. If you notice, it kind of comes out in these thin sheets. That's kind of what those 2D layers are. All right, so these are just different shapes. So a diamond is completely made of carbon. If you notice, this is the structure of it. Silicon dioxide, this is the structure of it. Silicon carbide, this is the structure of it, right? And then graphite, okay? And then you have molecular. Molecular is held together by van der Waals forces, which are relatively weak intermolecular forces, okay? So that's just the LDFs, basically. Okay, our London dispersion forces. All right, so in our ionic, you're going to have a low vapor pressure. Okay, you're going to have a high boiling point and high melting point. So remember, low vapor pressure is literally because if I'm turning from, right, I need a high melting point. That means it takes a lot of heat to go from a solid to a liquid. And then I have a high boiling point. That means it takes a lot to go from a liquid to a gas. So it makes sense that the vapor pressure, because I need so much heat to go from a liquid to a gas, the vapor pressure is low because I'm not going to have a lot of gas being formed. Vapor pressure is literally the pressure being created by the gas that's being formed. Okay. So ionics are not conductive when they're in solid form, but they are conductive when they're melted or aqueous. Okay, and in case you don't remember what aqueous means, keyword, aqueous means when a solute is dissolved in a solvent, right? So it's a solution. Okay, so aqueous, and the solvent is water. All right, so metallic can be alloys held together by the mobile sea of electrons. The vapor pressure is going to be low. Again, it's usually really hard. But the melting point and boiling point can vary depending on the metal, okay? So we're not going to just jump and say they're all high, but it does take a lot to turn them into gases, okay? Then you've got your network covalent. So your vapor pressure is low, your boiling point is high, your melting point is high. They're non-conductive. So of course, hopefully we're noticing a pattern, right? Ionics, and this makes sense, they're non-conductive in solid form, conductive when melted or aqueous. I'm going to add this in now that we're looking at a metallic, right? Metallic bonds are conductive and covalent, non-conductive. Here's where that comes into play, right? Non-conductive, conductive, non-conductive. Non-conductive in solid form, conductive when melted or aqueous. So I'm going to repeat that because here's what I need you to hear. Non-conductive when combined, so think salt, okay? It's not conductive when they're in salt form. But if I put salt into some water and make an aqueous solution, okay, of some salt water, it can become conductive. And that's because when things are in aqueous solution, my positive ion and my negative ion actually separate. So now I can create that charge I need, right? So, all right. Molecular covalence, usually a higher vapor pressure. Okay, that's what generally means, that typically, right? But that does mean there can be some exceptions. Boiling point low, melting point low. So those are super easy to turn into a gas, and they're not conductive either because they're covalent. Remember, covalents don't have any conductive properties. All right. So polymers. Sometimes these molecular solids self-assemble to form a polymer. Hopefully you remember the word polymer from when you were learning biology. All right. So a polymer is a large molecule made of repeating units. Okay. And here's a picture of a monomer, a small molecule, a polymer, a long chain molecule made up of a repeated pattern of monomers. Okay. You learned this in biology, so hopefully you remember it. Polymers are made up of a large number of simple molecules called monomers. Some examples include plastics, cellulose, carbohydrates. Polymers not only have many uses in synthetics, but also in biology. Proteins are biological polymers made of the monomer units of amino acids. Okay, so the monomer for a protein is an amino acid. Okay, the polymer for a protein is essentially the protein itself. Okay. So the base is the amino acid, the protein itself is the bigger piece. Okay. All right. And then here are some examples. Okay. And if you notice, these are actually called polypeptide chains. So proteins form polypeptide chains. Okay. Which makes sense. Okay. An amino is bonded with the peptide bond. These peptides bonds happen every single time between every single monomer. Lord, y'all, I'm having time, which is an amino acid. And then that forms one long polymer, which is called a polypeptide chain when we're talking about protein. Okay, so what should you be able to do with this? You should be able to identify the type of solid given either the formula or properties of the solid. You should be able to use IMFs, inner particle forces present in pure substances, to explain why physical properties, melting point, boiling point, vapor pressure, etc., vary between the two named substances. You should be able to use representations of ionic, molecular, metallic, and network covalent solids to justify their properties. And you should be able to compare and contrast the properties of ionic, molecular, metallic, and network covalent solids. All right, so now on to the last little bit, and this is pretty short. Solids, liquids, and gases. Represent the differences between solid, liquid, and gas phases using a particulate level model. So you see how short this is, right? So in this image, and I know I'm kind of covering it a little bit, but in this image, when we're talking about viscosity, right? Viscosity is basically like how thick or sticky a liquid is, right? So it explains it up here a little bit. This is a property. This is a physical property. So the more viscous a substance or a liquid, the thicker that liquid is, okay? So it's just giving you an example by showing you the length of the drop. It's also giving you an example by explaining that the stickiness is caused by stronger or more numerous molecule to molecule interactions, which cause the molecules to stick together more when pulled upon. In cooking terms, the more viscous solution can appear clumpier, and a less viscous solution will look runny. So, of course, they go from water to chocolate syrup. And if you look at the picture, right, what's really important down here is they're showing you, like, for a heavy syrup, I can manually stretch it and change how it looks. If we get down here into the oil and light syrup, the distance is weakly bonded water infill. So it's basically like not strongly connected to each other, right? And I just so you can see for comparison, of course, they have just plain water over there with some stuff in there. If you notice, even though a lot of these things don't necessarily mix with water, water molecules are somehow embedded in most of these pictures. So it's pretty important to notice. And that's when you get down to your light syrup, your heavy syrup, and your chocolate syrup, right? So this is important. It's just kind of showing us the different properties that we may notice as in a liquid as it becomes thicker. So a thicker liquid doesn't mean like, oh, it's almost a solid. It's not the same thing. It's just showing you that that is one of the properties you need to understand about liquids is viscosity. All right. So as we compare solids, liquids, and gases, of course, we've already seen this diagram. You've seen it a million times. You want to make sure that you understand that in a solid, the particles have a regular arrangement. They vibrate in their fixed position, so they don't actually move, but they do vibrate. Okay, so atoms are never really at rest, including in the human body. Our atoms are in a regular arrangement, right? It's a fixed arrangement, but they're constantly vibrating in that fixed position. They're super close to each other. All right. Oops, sorry. In a liquid, the particles are randomly arranged and they actually move around each other, right? So they're not just sitting there for vibrating, and they're close to each other, but they're not necessarily as tight as they would be in a solid. And then the gas randomly arranged, moving quickly in all the directions, they're far from each other. So really quick to kind of highlight that, we're going to take a look at this example. So, right, we're going to start with a substance we know really well. So if we look at water and we start with water as a solid, and let's see if I do water as a solid, right? Okay, and then let's say this is just so you can see the temperature. So of course the temperature is in Kelvin, but they also have Celsius for you. All right, so this is liquid water. If you notice, the temperature up here is increased. This is a gas. Okay, so you see the temperature differences, right? Just so you can see it. Okay. All right, so now this actually allows me to take it. It's in a solid form, so now I'm heating it up. So if you notice, when I heated it up, what's starting to happen to my water molecules. Now you see how it's getting into the gas form. So remember, substances can go straight from a gas from a solid to a gas, and they can go straight from a gas to a solid. They don't necessarily have to enter liquid form, because sometimes we forget that. So if you notice what I'm doing, and it's taking a while, is I'm cooling it down. It is taking some time. It's not something that happens instantaneously, right? And now it's back in the solid. So if you notice in the solid, they're just vibrating in their spot. In the liquid, you'll see that they're kind of moving around each other, right? As I heat it up, it's still actually taking a high temperature. And I don't know if you looked at the temperature itself, but it's still taking a high temperature for it to actually end up as a thing. It didn't take quite as long to turn it into a solid. Okay. And then if we go from gas form, it's already hot. So heating it up is just going to make the gas move faster. This is cooling it down to kind of cut the movement some. Okay. So as you can see, even though I stopped cooling it off, the temperature is now enough that it's now closer to a liquid form. Okay. So same thing can happen with any of these. So this is oxygen gas as as itself. This is oxygen in liquid form. This is oxygen as a solid. Argon, and the reason these are important, oxygen is one we commonly use. Argon is a oh my gosh, guys, noble gas. So it doesn't really interact much with other things. But because it naturally exists as a gas, this is one where it doesn't. You see, I hit liquid and it's turning itself into a gas, even though I just hit liquid. Okay, so this is that low vapor. This is that high vapor thing, right? Like when we say the high vapor pressure, this vapor pressure is already vaporizing and we haven't done anything yet. It's supposed to be in liquid form. Okay, and then of course this is gas. So this is kind of the difference between them, if you can kind of see that, right? Neon as a solid, neon as a liquid. Again, this is a noble gas. It's not as large as argon, but you see the same thing. It's already starting to attempt to vaporize itself, even though it's not in solid form. Like you see, it's literally, the temperature is only 28 Kelvin, right? It took us to 400 and something to get water to do even anything close to this. So that's really the difference when you're looking at these different properties, okay? All right, so can you now explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interactions between these particles? And can you represent the differences between solid, liquid, and gas phases using a particulate level model?